want to do like a little series about JSON performance considerations. Examples would be indexing or storage choices. And I want to limit the number of concepts I introduce in every presentation here because they go on YouTube and people, I think, don't want to watch like an hour-long video. It's better if we keep to 20, 30 minutes. So I've prepared a bit regarding this, but we could also make this and ask me anything. So if you have questions, feel free just to put them in the chat window. I think you're all muted. So just write something in the chat window and Blaine will then read them out aloud to us.
Yeah, if you're not familiar with where the chat window is, if you hover over the Zoom window, you should see a bar either at the bottom or the top with a little chat bubble on it.
Right. Okay, so you take care of the chat, then I don't have to look at this. Yeah, this is then a topic that comes up quite often about performance. Either people are not happy with performance or they want to make sure that everything they do is best suited to get the optimal performance. So the first thing is about storage. As you know, probably we have different data types to store your JSON in, being varchar2 up to 32K, or clob and blob. Generally, the recommendation is if you know that your JSON is rather small, just pick a varchar2 data type. For most people, that's not possible. The average size may be just a few Ks, but typically they may have outliers, which can be up to 100K. So they cannot leverage varchar2 here. They need a lob, a large object. And most people at this point pick clob. That seems to be the natural choice. Since JSON is a text, then they use the character large object. But the thing with that is that it typically uses 2 bytes per character, unless you use a single byte character set, like an ASCII character set, which most people don't do. They run a Unicode or a UTF-8 database. The clob will not be stored in UTF-8. Instead, it's stored in UCS2 or UTF-16. And the consequence is that you're using 2 bytes for every character. The reason for that is that on a normal character string, let's say a long text, you may want to jump to an offset. Let's say the 200th character. So if you know you use 2 bytes per character, you just jump to the 400th byte and you have the data you want. These kind of operations typically don't make a lot of sense on JSON. You rarely want to jump at a given position. Normally you parse the entire JSON. So if you, instead of clob, choose a blob as the data format, you can directly store the UTF bytes. That means that for every ASCII character, you only use 1 byte per character. So UTF-8 is a variable byte character set, meaning a single Unicode character could use between 1 and 4 bytes. But the nice thing is that the ASCII characters only use 1 byte. So storing your data as a blob cuts your I/O in half. That's already a big thing regarding performance. Now you may ask, how can I print this? If I select the blob, I don't see the actual value. There is this toClob SQL function. So here in the example, we use a toClob, and this call is your blob input. And this will print it, this will convert it to a clob, and you can use that to print it in SQL+ or SQL Developer. So the general recommendation here is use a blob. We also do a lot of inlining. So if you read a lob from disk, we inline the data up to, I think, 4K, 32K, depending on what stack you're using. So you get similar performance compared to a varchar2. So if the other question is, if you're on lobs, one question that people typically forget is, should I inline my JSON data or should I store it out of line? This is possible for lobs to choose. I believe the default is inline. What does it mean, whether you store your lob data in line or out of line? So what it basically means is, are you storing your JSON content together with relational contents in the same blocks? So that's the inline storage, which means that for your relational content, since you mix it with your JSON content, if you just scan your relational fields, you have to read more blocks. So if you primarily access the relational parts of your table, then it would make sense to store the data out of line, or even store it in a separate table and just use joins to join your relational table with a JSON table. So I can give you one example where this might come handy. This is if you have a relational application, maybe even an older legacy application, and you just want to get some flex fields, so some additional data for your rows, and you choose to use JSON for that. But the vast majority of your access patterns wouldn't go towards your JSON field, but rather to your relational field. So in this case, either store your data out of line or store it in a separate table and use joins to find your JSON data. So that is briefly covering your storage option here. If you have questions, just put it in the chat and we can answer them right away here. The next thing I wanted to talk about is the JSON check constraint. So we have not added a JSON data type in the releases that are available now. So you use the data types that are listed here. blob is the recommendation. And you tell the database that the content is JSON by adding this isJSON check constraint. So what happens if you have this isJSON check constraint? Every time you do an insert or update, we're gonna parse through your JSON record and make sure that it's syntactically correct. And unfortunately, JSON parsing is quite expensive. And the reason is that we have to really go byte by byte to make sure that the order of brackets, for example, is correct, but also to find escape characters. So for example, if we have a double quote, that may not necessarily mean that this is the begin or end of a string. It could be inside some escaped character, for example, or it could be an escaped double quote. So this is why parsing is inherently expensive. But there is a way of keeping your check constraint, which also enables the simplified syntax and the data guide and log caching. So there is still a lot of benefits of having the check constraint. But if you're certain that your application guarantees that only correct JSON gets to the database, you can just disable it. So this is the statement here, alter table, disable constraint. So the constraint is still there. Your JSON dictionary views will still list that column as JSON, but you don't pay the price of the evaluation of the parse every time. Actually, but at this point, you really have to be certain that your application is not inserting junk into the database. So at this point, the database will not do the syntax check for the JSON you insert.
There's a question in chat.
Yeah.
The NLS character set is a whole bunch of numbers and letters.
Okay.
Will the blob use 1 byte per character? WES or WE8IS or ISO 8859P1 is the character set. Not familiar with that.
This is Western European, I guess. If this is a single byte character set, I guess it is 1 byte per character, yes. So don't cite me on this, but I would say since it's single byte, it's the Claude uses it. So it's only for multi-byte. And what we see and what we recommend is to run AL-UTF or AL32 UTF-8. That's it is. So that's the Unicode database. And if you use AL32 UTF-8, then your CLOP data will use 2 bytes per character. The other issue is, I mean, this is a good question. So if you run this Western European character set, you are using 1 byte per character, but you are encountering character set conversion costs because all our processing is done in Unicode. So whenever we read the log data, we convert it into a Unicode sequence. I think one example is the euro sign. I'm not sure if the euro sign has been added to this character set. So for most of the time, it's not that costly, but there are some characters in this character set that will have to go, that will be converted to Unicode, to UTF-8, because all the JSON processing happens in UTF-8. So even then, it's still beneficial to store your data as a blob. Okay, any more questions regarding storage? Otherwise, I will just continue sharing. And wanted to do a bit on indexing for a long time now, and I think today's the time where we start with indexing. And there are basically two true indexing techniques. We will come later to other ways of optimizing, not in this AskTOM, but in the next one about in-memory and about materialized view. But here we're really talking about indexing. So we do have functional indexing and JSON search index. And I want to put them here side by side and explain the differences in what they can do and in the differences in the concept and at what cost these features come. So the functional index is using a B-tree data structure. So you can find a key in logarithmic time. So this is decade-old technology, probably since the 70s, I would guess. So it's best for point queries. So you have to know the fields that you want to index. And for that specific field, for example, the ID of a customer or a zip code of an address, you create an index.
Beta, right now I think you're showing the notes view of your slide.
Oh, is that true? Okay. Interesting. Yeah.
So and while you're switching over, there was a question that said, did I understand it correctly that even when you choose the AL32 UTF-8 character set, that clogs are not stored as UTF-8, but as UTF-16?
That is correct. That is correct. If you use AL32 UTF-8, your CLOP data is not stored as UTF-8, but it's actually not UTF-16, it's UCS2. Don't ask me about the exact differences. But for the sake of this discussion, we might as well call it a synonym to UTF-16. So it's 2-byte characters, yes. Okay, now I'm going to just share my desktop and is this now visible?
Yes.
Yeah. Okay. Now it's getting black.
Now it went back to now we're back. Okay.
Now we're back. Okay. So let's start again. I want to put side by side the functional index and the JSON search index. So functional index requires you to specify which fields to index: the ID of a customer, the zip code of an address, etc. And we're executing a function, in this case a JSON value function, to extract one value per row or per JSON document. Then this value is being put into the B-tree data structure, which allows us to find it in logarithmic time. And if we found it, it's associated with a row ID, and we can go back to the database and ask for a row given that row ID. That is quite basic and simple. And the JSON, the functional index is always strictly typed. So you have a B-tree whose keys are numbers or varchars or dates or something like this, but they cannot be mixed. So in JSON, it's possible that a field may have different data types. We may have a value of an ID being a number in one instance and maybe a varchar or a Boolean in another instance. That schema flexibility cannot be preserved in the functional index. So you have to pick a data type using the returning clause to make sure that every value conforms to the same data type. And this is actually quite obvious because you want to be able to do range queries. And as you know, if you sort something alphanumerically or just numerically, then things may come at a different order. So 2 is greater than 11 if you sort it alphanumerically. This function index can be used for JSON value, and JSON exists on these indexed paths. If you have a JSON value with a path expression where there is no index, it won't get executed using an index. And the maintenance increases linearly with the number of indexes. So if you add more and more indexes, your costs for every update or insert will increase. So the question is, what is a good number of indexes, or where should I become careful with adding more indexes. That obviously depends a lot on your ratio between updates and queries. If you only do queries or very rarely do inserts, you might as well have a large number of indexes. But if you have like a mixed workload or a workload where you also have a significant number of updates, deletes, and inserts, then that is something to consider. So generally, I think up to 10 or 15 indexes, or let's say between 5 and 15 indexes, this is faster than the JSON search index, which brings us to the next index. So the JSON search index uses a different underlying data structure, which is posting lists. It's based on the text index, but it has been made aware of the path. So it is not text indexing the entire document. We're not just running a text index on the document. Instead, we have information about where or under which path expression the value occurs. So we can then look for a value in a posting list and join it with other information about the position. So this index allows us to index an entire document. There is right now no choice to pick the paths you want to index or not index. That's called path subsetting. We don't have that at the moment. So it will index the entire document. So this is something to consider. Let's say you have just a few fields you want to index with this index. It will still index all the other fields you know will never be used in queries. So that makes it a bit slower to maintain. So insert and update will take a bit longer than a single functional index. But the question is how many functional indexes will come at the same or similar cost than the JSON search index. That's again this number 5 to 50. The other benefit of the JSON search index is since it relies on the search index technology that you can use full text search operations or near that you can't do with a normal functional index, which only allows equality or greater and smaller. So this index can be used for JSON value, JSON exist, and JSON text contains on all path expressions. And the optimizer prefers the functional index. So if you have both the functional index as well as the JSON search index, it will prefer the functional index because the logarithmic time to find a key is always faster than the JSON search index. So this is the concept question. I now have created a script in LiveSQL where we can actually look how this can be done. And this is a public script, so you can try this at home. You should be able to find it if you look for JSON indexing. There's a typo, I will correct this, functional indexes and JSON search index. So that's the script I've created. So let's go through some things to consider if you create especially the functional index. So let's just run the script and then we can slowly go over it. So now I was told if I click on my session, then yes, now this is here and we see the output. So what I do here initially, creating a plan table, that is just to be able to do an explain plan. That's still something that seems to require workarounds in LiveSQL. So I've created just this plan table here. And this is the table where we store our JSON data. I've chosen a varchar 32K as the data type, and I've added in this JSON check constraint because I'm using the simplified syntax. Now I'm inserting just 3 rows. I tried to keep it very simple and crisp to convey the concepts. So all our 3 documents will be a JSON object which has a key A and a key B. And we see here that A has 3 values, 1, 2, 3, whereas B has a scalar value here, but then this B has a collection or an array of values here. That is to show one of the limitations of the functional index later. So we commit this, and I'm using now this simplified syntax here just to select the documents, and this here relies on the presence of these JSON check constraints. So when we do semantic analysis of this query at compile time, normally there is no .a and j called, so this would be a compile time error message, but because we have told the database that j call is JSON by using this JSON check constraint, I can now dot my way into this. So if I would put like an X or a Y here, which would not occur in the data, I would not get an error message. Instead, I would see a null here in the A column. So we see here the value for A is being extracted. The 2, the 3 is here. If we do the same now with B, oh, by the way, if you play with a simplified syntax, you always need to alias this expression. So if you just say jcall.b, it wouldn't work. You have to say t.jcall.b. So this is the alias. So again, so here is your alias. Your table is called t, and I gave it the same alias t. I like it short. I know it's maybe not so easy to understand, but then this refers to the alias. So this is my table alias, this is my column, and this is now a field name inside my JSON. This is the A, so we see we extract the values out of our J column. Now if I do the same with B, it's basically the same for the first and the last row, but in the middle we see here the B is an array of 2 values, and we see that that is being returned as this array. So the simplified syntax or dot notation is not yielding us single values. It yields us basically whatever we're selecting. It's returning whatever structure we're selecting. It could be one value, it could be, in this case, it's an array, or it could be a nested object or a whole nested substructure. The other thing is, what we don't see here, I would have to do a describe, is that the return value is always a varchar2 4000. So although we're returning numeric values here, we don't know that at compile time. So if we build the SQL query here, we have to define the return type of A before we looked at all the instances, at all the JSON. And JSON can be semi-structured. There could be another A, which is a Boolean or a string. So we basically coerce all the values into a varchar. But here we want to do, or we want to treat these values as numbers. So that's where I use the full syntax, the JSON value syntax here. And that is also the one that you should be using to create an index. So the equivalent, or more or less the equivalent of this t.jcall.a is this JSON value. Your input is the JSON column. This is your path expression. This is optional, the returning number. The default, again, is a varchar2 4000, but since we want to have it as a number, I type this out here. So that is the syntax that's standardized in SQL 2016, whereas the simplified syntax here, that is something that Oracle or that we came up with. Good, so we see that these values got returned as numbers. Well, it's hard to tell here in the output, but we can now use the same expression here in the where clause. So I moved, instead of the select, I just moved this JSON width value in the where clause, and I want to find out where the number is greater than 3, and I see that this document got selected. A is greater than 2 because it's 3. So now let's look at the plan of this. We haven't created any index. So this is my not so beautiful workaround. So I have this explain plan for this query. I give it an alias, and then this lengthy thing here, we can ignore this for now. I'm basically just looking out for this JSON plan. So that's what we're interested here. Down here, we're doing a table access, and we do a full table scan. So no index. So let's create an index. It's a functional index, so I create it on this table T, and inside these parentheses, I give the functional expression that is used to populate the index. Well, this is our JSON value statement. JCall is a column of T. $.a is the path expression we're evaluating, and we're returning this as the number. So we're going to populate our B-tree index with number values. So if we just repeat the same query in our explain plan, we see that our index was picked up. Well, that was quite easy. So what is there really for me to tell you more? Well, there is a bit more. So this always works if you use JSON value in the where clause. It's the same expression you use to define the index. So if you use this in the where clause, the index should get picked up. But there is another way to express a filter in JSON, and this is JSON exists. So JSON exists takes a path expression and sees if this path expression selects at least one value in your JSON data. And this syntax is a bit odd. I'm explaining it. So we're looking for a node which has this property. So the question mark indicates that we have a filter or a predicate to evaluate, which means given the current node, which is our topmost, or which is our entire document, go to the A field and compare it with 2 and make sure A is greater than 2. So the question is now, well, this looks quite complex. Why has this been done? Why can't I do all my comparisons in using JSON value? And the difference is basically where you do the comparison. So here, using JSON value, you're doing the comparison in SQL land, meaning you're pulling out a value from your JSON, and then you're comparing it with a SQL numeric literal here, and the comparison is done in SQL. But this means in SQL, you can only compare scalar values. You have one value on the left. This is the output of JSON value, and one value on the right that you compare. But inside JSON, we're allowed to have arrays. Remember this B array had 2 numbers. So the predicate here will actually iterate over the array. So this allows us to check or to compare this 2 with multiple values in our JSON. So the cardinality does not have to be 1. So there is an implicit for each iterator built in here. So that doesn't really apply because all our A values so far, I'm just scrolling back here that we see the values that I inserted. So these are our A's. They happen all to be singleton values. But for the B value, that's different. Here, B basically has 2 values. So JSON value could not yield us these 2 values, the 3 and the 4, because JSON value is forced to return 1 value. It's a SQL operator. With a path predicate, I could scan this array and say, well, give me all the B values, or give me the documents where B is 3 or 4. That's the motivation for JSON exists. So we're running this JSON exist. We look for A greater 2. We get the same result back. But what about our index? Were we able to use the index? By the way, there's something in the chat. Should I stop for a second, Blaine?
I think it's a conversation going on. Go ahead and read it just real quick.
Okay, that's fine.
Missing the point.
So we have not used our index. We have an index on A. We have a query on A, but we're not using the index. And why is that the case? Well, that's exactly what I said, because our index can store only 1 value, whereas this JSON exists would be able to operate on multiple values, so we're not using the index here. But there is a way to enable the index to be used. So we're dropping the index again, and now it's getting a bit detailed, I would say. So now we're recreating our index. The path expression is the same. Our returning clause is the same. But now we're adding these optional keywords here. Error on error, null on empty. So this is now, by the way, this is all standardized. So don't criticize me on the terms, although I think we were heavily involved in defining that. So null on empty means if $.a does not select a value. Remember, in JSON, not every JSON document must have an A field. There could be fields where this is missing. So if this is missing, meaning our result is empty, then return a null value. Don't raise an error, just return a null value if you don't select, if you don't find a $.a. For all the other errors, let's say you find multiple ones or the number cannot be converted to a number, then raise this error. So again, if I run this JSON value on an input JSON where $.a is either or if it's present but not a single value, it will raise an error. So that means that this index can only succeed if A points to either missing values or single values. We will later see it will fail if we apply it on B. So now Oracle sees that this index has been defined with arrow on arrow and null on empty. And now our rewrite of JSON exists with this path predicate will use the index. So this is what we see here. We're repeating our JSON exists, and all this boilerplate is just to print the plan for this JSON exists. And we see it has been created. Just need a drink of it. Oh, sorry, the index is being used. The index scan is working. So this is something to take away from this discussion. If you want to use JSON exist, or in general for this, for the JSON value-based search index, use arrow on arrow, null on empty. So now, obviously this means that I cannot insert any further documents where A is not a scalar value. I could insert a document where A is missing. So if this was X, it would be perfectly fine. There is no A. The null on empty will make the JSON value return a null, and the null goes into the index, but I cannot insert this array here. JSON evaluated it to non-scalar value, and the index couldn't handle it, so this insert gets rejected. So let's look at our B column. So here with B, we see this odd thing where B points to an array of 2 values. So the simplified syntax will just return this as an array. This doesn't make any sense to put in an index here because this is just a string or a varchar. This is open parentheses, 3, 4, close parentheses. If we would put this value in an index, I mean, we probably could, but then it would not compare with 3 or 4 because it would do a varchar 2 equality comparison and not going over the array and looking for a value. So we attempt to create an index on B, and for the very same reason, the JSON value raises an error and the index creation fails. So no way to create this index on B if B is not a scalar value. There is a workaround, which is that instead of arrow on arrow, you give it a default value where you say, well, don't raise the error, give it this odd number here or this string like a 0 I've chosen on arrow. Then the index creation goes through, and we could select it, or the index would get picked up. If we use the exact same syntax here, we see a range scan happens. But now, if I just look for the default, I think I have to make this a bit smaller here. Right here. So now we're looking for the value 0, and we actually find the document. And the reason is that the error has been masked as a 0. So this is a possibility that may make sense in some cases where you know that you have these kind of outliers and that they are not relevant. So you would say, well, only the scalar values make sense. If they're not scalar, they're garbage, so I might as well mask them away. That might work, but I think that's really a corner case. So what's the way out here? I think it is quite common to see JSON instances that have fields which point to multiple values. One example is you have a customer JSON record, and a customer typically has one address, but then there are a few customers who have multiple addresses. Let's say a home address and a vacation home address. Each of these addresses has a zip code, and you want to search based on zip codes. So your index on zip would fail because of the few people that have multiple addresses. So for this, you could create the JSON search index. This is the other index structure based on the posting lists. This is the syntax. You create it also on T and on J call, and you say this for JSON so that the search index knows that the text it's indexing is actually JSON, so that it knows how to treat the different paths or the different containers, the arrays and objects. We want to drop our functional index here because the optimizer would prefer it over the JSON search index if it could. So now we're running our same query here that we could not support using the functional index. It's our B value, and we want to compare it with 2, and we see that the search index works. And the same is also, so this is the JSON value example, and the same would also work if you use JSON exists with this path predicate. Then we also see that the JSON search index is getting used. And next time we can do a bit more about the properties about search index. I wanted this presentation here to cover and explain the complexities regarding the functional based indexing using JSON value and what it means to have different cardinalities in JSON and kind of the problems that come with that. So if you have a UTF-8, or let's say you have a single byte, or single byte, the AL16, no, what was it? That was the other example, the Western European. The Western European 8 ISO, blah, blah, blah. That will be on disk, and it will also be the database character set, and then it will get converted to UTF-8 when we process it in JSON. So now if you have AL230, if you have the UTF-8 database, that's the database character set. It's still not storing that on disk. It will convert it then also to UTF-8. But you're undergoing the costs for all these conversions. And that's really, I think the message here is use blog, because then you don't have to worry about all these things. Also, if you, let's say, import and export your database from one to another, and that has a different character set, then you kind of get the same performance if you use blog. If you come from a client like Java, I think it makes even less of a difference if you use CLOP or blog, because you're not selecting the value and printing it to a screen or something similar. You typically bind it to, you're binding it to a programming language variable. Has Oracle introduced any new features on 18C compared to 12C? Yes, so we've added performance improvements, especially in the lob layer, and we also added support for lobs in the return types. So you can now do JSON generation returning CLOBs, or JSON value or JSON query returning CLOB.